Today, we will be discussing the third lab of Physics 2211. This lab deals with determining the unknown mass of a black hole. The objective of this lab was to find the mass of a black hole in GlowScript, a computation model program that uses Python. In order to do this, we had to apply Newton's second law of motion and law of gravitation to calculate the unknown mass. We are given a unique trajectory of a star orbiting the black hole, and we must analyze this motion using Newton's second law and Newton's law of gravitation to calculate the black hole's mass. I altered the startup code to be able to do so. The alterations will be shown later in the video. We are able to calculate the mass of an invisible unknown object by simply analyzing the motion of a star, which is pretty cool. My results show that the mass of the black hole is 9.73898 times 10 to the 34 kilograms. In this lab, we will be using two equations, Newton's second law and Newton's law of gravitation. Newton's second law is force equals mass times acceleration. This can be derived further into the equation, the change in momentum divided by the change in time equal to the net force. This equation is used to show the relationship between F net and the change in momentum over the change in time. The equation will be used to calculate the net force, which will then be used to calculate the mass of the black hole. Note that the change in momentum of the star is the effect of the change of net force acting on the system. While they are equal to each other, they are different concepts. In this situation, we are to assume that there is no other force acting on the star besides the gravitational force of the black hole. With this assumption in mind, the mass can be calculated using Newton's law of gravitation. It is manipulated to calculate the unknown mass, which can be seen here. Here, you can see the initial conditions I set for my system. The mass of the star was given and is 2 times 10 to the 30 kilograms. And we are told to set the delta t as 1 day time. So that is set here in the seconds. Below you can see the code that is used to find the x and y components of velocity. Now you can iteratively run through all the position values given to calculate the necessary variables. Using the x and y components of velocity found, we can calculate the initial and final velocity here. Then, to calculate the initial and final momentum, the code multiplies the mass of the star by the velocity. With that information found, the change in velocity and the momentum is found by subtracting final by the initial value. dp dt is calculated by dividing the change in momentum by the change in time, and with our understanding of Newton's second law, we know that dp dt is equal to F net. The parallel and perpendicular component of dp dt is determined by the following calculations. Finally, to calculate the mass of the black hole, Newton's law of gravitation is inputted. The r-squared value is found by subtracting the magnitude of the black hole's position from the star's position and squaring that value. We input that into the code that represents Newton's law of gravitation to find the mass of the black hole. The following code sets up the arrows that will be used in the computational model to represent F net parallel, and F net perpendicular. Here is the computational model of the star orbiting around the black hole. You can see that the red arrow is pointing towards its origin at all times. This is the F net arrow, and that gravitational force is the only force in the system. Also, we can observe the black arrow, which represents dp dt parallel. It is always parallel to the star's motion, or anti-parallel, as this arrow depicts whether the star is slowing down or speeding up. The blue arrow represents dp dt perpendicular, which causes the star to change direction. With all of that information in mind, let's consider some conceptual questions. What if a different black hole were to take the place of this black hole? If the current black hole were to be replaced with a different black hole, but the motion of the star remained the same, then it would not be possible to tell the difference, as the mass of the black hole would be calculated to be the same. This is because the mass and the motion of the star remain the same, and this is what is used to calculate the mass of a black hole. Therefore, we are not able to calculate a difference in the mass of the star. Earlier, we noted that the change in momentum over a change in time of the star is the effect of the change in net force acting on the system. While they are equal to each other in the momentum principle, they are different concepts. F net is found by taking the sum of all the forces on the system, while dp dt is found by analyzing the object's motion. By knowing there is a change in net force, then there is a change in momentum. If we were to know how the momentum is changing, then we will know the net force of the system. The momentum change is caused by the net force.